Hello, everyone, and welcome. My name is Liz Pemper, and I'll be your moderator for today's WJE webinar, Understanding the Causes and Significance of Facade Degradation. During the next hour, WJE petrographer George Reo and chemist Kimberly Steiner will discuss the effects of chemical incompatibility, staining, and degradation on a variety of facade materials, including glass, stone, metals, and coatings. Illustrated by case studies, they will describe typical field and laboratory investigation techniques and will offer recommendations for reducing the risk of degradation in your building facades. This presentation is copyrighted by Wiss Janney Elstner Associates. And now I will turn it over to Kim to get us started. Kim?
Thanks, Liz, and thank everyone for attending. George and I are really excited to talk to you about our chemist and geologist perspective on distressed to building facades. First, there are several learning objectives that we'll hope you'll get from this program. First of all, to identify primary types of facade material failure due to chemical incompatibility, explain how time affects material degradation, and understand some various field and laboratory techniques that might be useful, and how to reduce the risk of degradation to your facade. So we're going to talk about the description of our problem-solving approach, go over some case studies where we hope you'll get some snapshots of some field and laboratory evaluations. We're going to talk about what some of the laboratory techniques that we do, and we're not hoping that you understand the depth of the laboratory techniques, but just sort of understand that there are ways to understand some of these degradation mechanisms in detail that helps you understand what's going on with your building. And finally, provide some recommendations for reducing your risk of encountering distress. So when we're thinking about problems encountering building facades, as material scientists, we really think from the materials perspective. So we think that there's three different general mechanisms for which materials degrade. First is an adverse interaction with the built environment. And this can be related to temperature, freezing, exposure to moisture, the sea, exposure to nearby materials that may be incompatible. There's adverse interactions with chemicals that are used intermittently. So these are typically cleaners, or nothing that's part of your typical environment, but might be something that is used on the building once in its lifetime or periodically. And then additionally, there are problems just inherent to the material itself, where material may not be stable in a given environment or may alter with time, and that can lead to alteration and distress. So the general problem-solving approach that we use follows these steps. First of all, understand the history. So what happened and when did it happen? When was the building constructed? Were repairs done, and if so, when? When was the problem first noticed? Was it something that happened during construction, 50 years after the building was built? Did somebody say, hey, that doesn't quite look the way it used to? What's going on here? And if so, when? And there are a variety of ways to do that through, talking to people, doing some informal interviews, doing some field studies. You also want to understand the materials that are used, right? Because each material interacts with its environment a little bit differently. And different materials have different vulnerabilities. Some materials we think is very durable, and they are in most environments, but not in every single environment. So it's important to really understand from a materials perspective what they're seeing and what they're experiencing. Field studies are really important. Somebody needs to go out and look at the building. They need to understand what the distress really looks like. How many different materials on the facade does it encompass? How bad is it, right? Does it look aesthetic? Is it obviously severely structural? Or maybe you just can't tell from looking at it. But you can see where the distress is in relation to parts of the building. Is it on one face and not all faces? Or is it at a certain elevation? That gives you a lot of information. And then laboratory studies can be helpful to understand some mechanism and what's going on in case the history and the field studies don't give you all the information you're looking for. And with this, I'm going to turn it over to George to talk about some of our analysis methods.
Thanks, Kim. Before we discuss the methods that Kim and I use in the lab each day to solve materials-related problems, I'd like to briefly introduce the field of material science. Material scientists are scientists from many disciplines that have expertise in the composition, properties, and performance of materials. Kim is a chemist, so many of her projects involve understanding how material composition and chemical interactions influence a material's performance. Now, I'm a petrographer. Petrographers generally have training in geology or materials engineering and have specific expertise in characterizing stone and other manufactured materials such as concrete, specifically using microscopical and chemical analysis techniques. We generally begin an examination of the sample sent to us in the lab by looking at the as-received condition of the samples using various microscopes. This allows us to identify the components of the sample and also helps us determine what laboratory test method would be appropriate for the sample. To help understand variations in the performance of a material in service, we generally recommend subjecting materials exhibiting degradation to comparative microscopical or chemical analysis. This allows us to compare the chemical and physical properties of a sample exhibiting distress to a sample of the same composition that was minimally altered in service and hopefully resolve what's causing the distress. Some analytical techniques commonly used in our investigations include SEM-EDS, which allows for the high magnification imaging of materials and also allows us to collect the concentration of certain elements along the surface of the material that we're analyzing in the instrument. X-ray diffraction allows us to identify the crystalline components of a sample. And we also use various wet chemistry techniques like experiments you may have completed in a high school chemistry class to help determine the composition of materials that are soluble in various solutions. Our Xrs Spectrometer allows for the quantitative elemental analysis of inorganic or non-carbon-based materials to help identify trace metals or other compounds that could be contributing to distress of a material. Our FTIR instrument identifies organic or carbon-based materials, and our GCMS identifies and determines the relative concentrations of organic components composing a material. The big picture takeaway from our brief introduction of all these methods is that a chemist or a petrographer can point you in the right direction of what method to use after a discussion of the project concerns and initial cursory review of the samples after they're sent to the lab. It's often necessary to utilize various methods to come to an answer, and sometimes we'll pivot to an alternative or additional method as our investigation reveals more information. And now I'll pass it back to Kim to begin our first case study.
Thanks, George. So we're going to talk through case studies looking at 4 different kinds of materials. And we hope that you take from this an understanding that different kinds of materials may be vulnerable to different kinds of environments and some of the problems that can happen with these materials. We hope you learn a little bit about a materials analysis, but as I said, we're not trying to turn everyone into a material scientist in this hour, so we hope you enjoy our case studies. First one, talking about deposits on glass. So in this case, it was a mid-rise office building in the southwestern United States. And the problem they had was tenacious deposits in glass that were really unable to be cleaned with typical procedures. And they noticed these about a year after construction, so still fairly new into the building. And the photograph there is a picture taken from one of the offices through the glass, and you can see sort of the building next to it, but you can see those whitish sort of drip-like deposits on the glass that couldn't be cleaned off. So the client wanted to know, what are the deposits? How did they form? And more importantly, how do they remove them so that their tenants can look through clear glass again? So first we did some field studies and understood the construction of the building. So what we had are precast concrete spandrel panels and ribbon windows on part of the building. So the precast concrete had been lightly abrasive blasted to expose some aggregate. The windows were insulated glass units, and there was silicone perimeter sealant. So this was present on parts of 3 of the sides of the building. There was also glazed curtain wall present on parts of 2 sides of the building. So I'm going to skip to the chase here. You're going to learn that these issues are related to an adverse interaction with the built environment and a problem inherent to the material itself. So again, during the site visit, one of the most important things that we learned is that the distress is only apparent on the ribbon windows. It's not present on the curtain wall. So therefore, we know it's not the glass itself. We know that it's something to do with how the concrete, the sealant, the glass interact together with their environment. So during the site visit, we collected samples for laboratory testing. They were kind enough to have removed the outboard light of an IGU for us. They had it all created up, ready for us to ship back to our lab. We also took some scrapings from some windows so we can get some samples of materials from multiple locations. And one of the other things we did based on the site observations is it looked like those deposits were sort of drip-like features. So we wanted to understand what would happen with interaction with the glass and rainwater coming down the concrete. It was a dry day, so you see a colleague there taking some purified water in a spray bottle, wetting down that concrete until it dripped down, and then collecting it into a container so we can look at water that's run down the concrete. Okay, so as George said, one of the first things we do after a visual evaluation is look at it in the microscope and correlate what it looks like microscopically to what it looks like visually. So here on the right, you see a micrograph or a microscopical photograph of the outboard light of that IGU, and you can see this white material on the glass. And again, it looks pretty similar to what we saw in the photograph. It's little drippy, sort of semicircular type of features. And so now we wanted to do some additional analysis, so we put a sample of this into our scanning electron microscope to do some SEM EDS. So here, if you take that area, or an area like that outlined in the orange box, and put it in the SEM, we're going to get a lot more information. So on these particular SEM micrographs, in the upper left corner, you're seeing a lower magnification image. In the upper right corner, you're seeing a higher magnification electron image. And you can see that the electron image looks a little bit different from the optical microscope because you're just illuminating the sample in different ways. And then my favorite feature of the SEM is you can really pinpoint an area and get some elemental analysis. So at the bottom, you see some peaks, and each peak or each set of peaks associated with an element that's present in that given location. So in this particular sample, we're looking just at the glass itself away from the deposits. And we see silicon, calcium, sodium, oxygen. We see basically soda lime glass. So this is the typical kind of architectural glass composition that you're going to see in buildings all over the world. But now we want to look at the deposits. So one of the ways that we find it easy to look at deposits, and it depends. Sometimes it's better to look at it directly on the specimen. Sometimes it's useful to remove it. So in this case, we took the scrapings from the site visit, and here's a photograph of the scrapings. And you can see there's some brownish colored dirt, some black spots, but also these white fluffy materials that look like the white stuff we saw in the micrograph. So again, taking some of that material, putting it in the SEM, and there on the upper right, you can see the fluffy white material. We do the EDS analysis and see that it's primarily silicon and oxygen. We're not seeing much calcium or sodium from the soda lime glass. So we know that these deposits are a little bit different than the glass itself. Now, one of the concerns we have is that we know that there's a silicon perimeter sealant. And silicone is primarily silicon and oxygen. So it's going to look very similar by SEM EDS to the deposits. It could. And in many decades past, there were issues with silicone sealants that would bleed material out, that would lead to sort of a sticky surface that allowed dust and debris to collect. And we wanted to make sure that that wasn't happening. By the time this building was built, the formulations had been changed, and this isn't really a problem with silicones anymore and hasn't been for quite some time. But we wanted to be sure. So in this case, we wanted to use a chemical method that would really differentiate silicone from other types of silicon-containing materials. So what we did is we took a solvent that would dissolve silicone but wouldn't dissolve things like glass or dirt or debris, ran it down the glass and collected the material, and then analyzed it using Ftir spectroscopy. So here's some Ftir plots. In this case, each of these peaks is related to a given type of chemical bond. The main thing with Ftir spectroscopy is you can obtain reference libraries of hundreds of thousands of spectra. So you can match it to spectra to figure out what it is or figure out what it isn't. So in this case, the solvent rinse of the glass led to a little bit of detectable material. We know it's been outside. We know it's been exposed to a variety of different chemicals. But the important thing is if you look at the bottom spectrum in red, that's the solvent rinse of the glass. And if you compare it to the top spectrum in black, that's a reference silicone oil. And we don't see evidence of silicone oil in that solvent rinse. So we can stop worrying about any bleed out from that sealant. The other thing we wanted to look at is the rundown of the rainwater from the concrete and see how that might have affected the presence of these deposits on the glass. Because as I said, looking at it visually and microscopically, it looks like little droplets, little dried droplets. So the other thing we wanted to do is we wanted to analyze the water in the same way that we analyzed the deposits. And we know that the water has dried, right? The building was dry when we went there. It wasn't raining. So we took some of the water, we put it on aluminum foil, and just evaporated the water off and looked at the dried residue, again, using SEM EDS. So if you take some of that dried residue, you can see there's just some solid material that's left from the drying process. And looking at the EDS spectrum, we see a lot of calcium and oxygen. We don't see any silicon. We see aluminum also, and that's because we used the aluminum foil. But what we've learned here is not really a surprise to us. Portland cement concrete has calcium hydroxide present in the concrete itself, and that's water soluble, and that can leach out to varying degrees during rain events. And some of that calcium hydroxide will convert to calcium carbonate upon exposure to air from the calcium carbonate in the air. So it's very expected to see calcium in the solid deposits from rundown of concrete, but we're not really seeing anything else. And we're not seeing any silicon like we saw in our deposits. So if we look at our findings, we found that the deposits contain primarily silicon and oxygen, but were not residue from the sealant. And the water rundown from the concrete contains calcium. So how do we put this together? And this has a little bit to do with the knowledge of how these materials interact with each other and with their environment. So you see a little schematic there in the center where the gray material is the concrete, the precast concrete, and there you can see an IGU in the middle. So during a rain event, the water is going to leach some of that calcium hydroxide out of the concrete, and that's going to run down the glass, and as that water evaporates, it's going to leave some of that calcium-rich residue on the surface. And that's going to cause some additional initial deposition on the surface. And that is an adverse interaction with the built environment. But by the time we got to the samples, there really wasn't a lot of calcium there. It was primarily silicon-rich deposits on the surface. But what can happen with glass is if you have deposits on the surface, that can affect the glass itself, and during when those deposits get wet, it can lead to a slight breakdown of soda lime glass that can lead to very localized leaching of silicon from the glass, which then deposits on the surface as these silicon-rich deposits that we have. And that is just a problem inherent to the material itself. So then what did we tell the client, right? We already know that regular window cleaning will not remove the deposits, but by understanding the chemistry of what happened, we know for sure there really isn't anything, any reasonable chemical that could be used in a building that will take these deposits off. However, you can physically polish them off, and there are compounds and techniques for polishing glass to remove tenacious deposits or light abrasions from the window. So this is something that there are contractors that can do that can remove these deposits. The other thing the building owner needs to do is clean those windows at more frequent intervals so they don't allow the first type of deposition to happen, which can then lead to the second type of deposition, which is much more difficult to clean off. All right, now I'm going to talk about a case study of degradation of coating. Okay, so this was an apartment building in the Northeast US, and it had fiber cement rain screen panels on its facade, and they were exhibiting various kinds of discoloration. So the client wanted to know, what is the nature of the discoloration, what caused it, how do they clean it, and what is the effect on the building function? Because again, this was something that happened that was observed shortly after construction. So this type of distress was observed about 5 months after completion. They tried to clean it, and then they said it reappeared, which tells me if it reappeared exactly the way it was, it probably never actually went away, and it was just masked during the cleaning process as the building was wet. We were able to receive samples for lab studies about 1 year after installation, and we're going to find this as an example of adverse interaction with the built environment. So for our comparative lab studies, we were able to receive a reference panel that had been removed from the building, so had experienced the same general environment, but was not exhibiting distress. We also received a distress panel, and that photograph is on the bottom. There's some red arrows highlighting the distress. It can be hard sometimes to see certain types of distress or discoloration on a building. Sometimes it becomes very apparent under certain lighting conditions and certain viewing angles, but sometimes, particularly in bright light or viewing directly on, it can just sort of disappear. You don't see it anymore. So it can be a little challenging to take a photograph of a situation like this. So again, we're looking at it through the microscope. We're trying to understand what this material, what this distress looks like under the microscope. So here's a micrograph of an undistressed panel, and you can see it's sort of uniform in color. It's a little bit bumpy, but it's mostly uniformly bumpy. Again, we put it in the SEM, we look at the surface, and again, it looks pretty uniform. We're not seeing much difference, which is not surprising, right? Because visually, we're not seeing any differences in the panel. It's pretty uniform. We look at one type of distress, and we look at it in the microscope. And these lines are sort of light-colored lines, but when you look at it in the microscope, they look almost waxy or like a material has been sort of scratched on the surface. And again, we look at it in the electron microscope, and again, we see abrasions on the surface. Nearby areas are smooth and uniform like they are in the undistressed sample. And then we had a couple different types of distress. So we look at this other distress, which isn't so scratchy looking. It's a little harder to see. But we will look at that area in the SEM. We see sort of just these blotches of different kinds of material that looks a little different compared to the more surrounding darker colored material. And when we look at them, use the EDS to look at the elemental analysis. If we look at that circular patch in the center, the EDS tells us we've got a lot of silicon and calcium and oxygen and other elements that are very consistent with a fiber cement panel. So this is what we expect to see. And then we look at the more uniform area and we see a lot of carbon. We don't see a lot of other stuff. So looking at all this microscopical analysis, it tells us that what we have is actually a carbon-based or a chemically organic clear coating on the surface of these panels. And the distress that's visible is not related to distress of the fiber cement panel itself, but this clear coating on the surface. So again, being a chemist, I wanted to understand the chemistry of the coating and seeing if the coating was starting to chemically alter or if it was just being abraded and degraded through a physical technique. So again, we looked at FTIR, and you can see on the left-hand side, again, FTIR analysis. The bottom is our distress coating, and we took the spectrum, looked through library, and found it to be consistent with an acrylic coating. So an acrylic coating is not going to be particularly susceptible to environmental degradation in that environment within a year. It's compatible with a fiber cement material, so we're not expecting to see any degradation, but we want to make sure, so then we use GCMS to get a little more detailed information. With GCMS, it looks at the material in a little bit different way, so sometimes it's more helpful for looking at fine differences in material that can be associated with degradation. And here, each peak in the GCMS is related to one compound in the complicated mixture that is this coating. So the important thing is if you just sort of look at the peaks on the chart between the undistressed at the top and the two distressed coatings, they're all basically the same. So we're not seeing chemical alteration of the coating. So what we know, first of all, is that the fiber cement panels had a factory-applied clear coat. Now, nobody at the beginning of this project knew this. The architect and the building owners weren't aware that these were coated panels. They were expecting just plain fiber cement panels. The distress is related to microscopic alteration of the coating itself through physical means. The fiber cement panels are in good shape, right? They're not degraded or distressed, and the abrasion that abraded away the softer coating isn't causing abrasion or damage to the fiber cement panels. But cleaning is only going to add potential distress from abrasion. So what did we tell the client? First of all, we told them that they don't have a problem with how these fiber cement panels are going to function as a rain screen, but they have an aesthetic issue. And they need to work with the panel manufacturer to say, is there a coating that can be used to field repair these clear coats so that they have a more uniform appearance? They also needed to work with our contractors to modify their regular maintenance and window washing procedures so that the contractors understand that they're dealing with a much more sensitive building material than they probably thought just by looking at it. Okay, now I'm going to talk about some damage to metals. So this was a retail building in the southwestern U.S., and the problem was encountered during construction. There was discoloration of the aluminum windows and deposits on the masonry. So the client wanted to know, what is the cause of the discoloration and deposits? 2, how can it be repaired? And particularly since the building hadn't been turned over to the owner yet, who should pay for the repairs? This is often a either primary or secondary or tertiary question of our clients. You know, who's going to pony up the money? So the building was a tilt-up concrete panels that were faced with thin brick, and they had mortar joints that were applied in the field. There were some areas with eaves, some areas with cast stone, and anodized aluminum window. Now, they had recently cleaned the thin brick and the mortar to get rid of some of the mortar smears, and they used a strong acid, a hydrochloric acid-based cleaner. And aluminum and some of these Portland cement materials are very sensitive to these highly acidic materials. It's great for removing smears, but if you're not careful, then it can etch away your mortar, and it can pretty easily etch away and damage your aluminum if the aluminum isn't protected. So simply by doing some basic research into the history and looking at the building, looking at the pattern of distress, it looks like it's almost certainly the use of this cleaner on the building that caused this problem. But again, because the client also wanted to look for some financial resolution of the issue, they really wanted to have a lab report and somebody to tell them exactly what the problem was. So we were provided samples of aluminum and thin brick with a mortar for lab studies. And you're going to find this is an adverse interaction with the built environment and also the adverse interaction with the cleaner, with the chemical that was used intermittently. So again, lab studies, you're going to notice a pattern. We took a look at the sample, looked at it in the microscope, and then popped it in the SEM to really understand what's going on. So up there in the upper left is a photograph of a piece of the window frame that's severely damaged. And you'll notice that in the other picture you saw the windows were sort of a dark bronze brown color. And you can see that color in the two bottom corners, but in areas you just got this lightness to it. You've got that area in the center that looks silver. It looks pretty aluminum colored. So we're going to take that, look at it in the microscope, and yeah, we're seeing this sort of little half moon of silver aluminum, a little bit of brownish colored material around the edges, and this sort of thick, lighter colored stuff around the edges. So again, looking at it in greater detail and do some elemental analysis by SEM. And again, we can see clearly there's a deposit on the surface, and there's some areas that lack this deposit. By EDS analysis, we see the deposit is primarily aluminum and oxygen. Not surprising for anodized aluminum. The anodic layer on aluminum is an aluminum oxide layer. Often there's sulfur associated with the anodic layer because of the way it's processed. Here we don't see a lot of sulfur, but we do see a lot of calcium. And again, we've already learned that Portland cement-based materials can leach calcium from water in a rain event or in a washing event. So it does appear from this data point that there's some rundown from this masonry, and either some rundown or a little bit of spillage of the mortar can cause damage to aluminum, because aluminum is very sensitive both to highly alkaline environments like freshly mixed cement and new cementitious materials, as well as acidic materials like the cleaner. If we go to the area that looks more silver, we find that we basically just have aluminum. So in this case, the anodic layer has been completely eaten away by the chemical exposure. So now we want to understand the effect of the exposure on the anodic layer and the aluminum itself. So in this case, we want to look at it a little bit differently. Up in the upper left corner, you see an example of a window frame that's not so badly degraded. It's more uniformly dark brown, bronze in color, but you can see some rainbow colors that are associated with some distress. In this case, what we did is we cut it, and we want to look at in cross-section. So we want to look at the thickness of the aluminum and look at that thin anodizing coating on the surface to see what's going on. So we prepared what's called a polished cross-section. So in this case, we cut a piece, we embed it in that circular puck of resin. That's just to make it easy to polish a very smooth surface so we can look at it in great detail in the microscope. So if we take a sample and then just look at that surface, right? So we're not looking at the aluminum so much as we're looking at that anodic coating. And you can see that micrograph up there at the top. And I'm sort of outlining the anodic layer in those squiggly yellow lines. And you can see with that one arrow in the center that there's a big old pit or this crevice in the anodic layer. It hasn't gone completely through in this area that's not severely degraded, but the anodic layer is barely there and isn't able to function as intended as a protective layer on the aluminum. Now we compare that to a more severely degraded sample where we have some evidence of the aluminum coming through and much more distress. Now here we're going to do the same polished cross-section procedure, but here the image I'm going to show you is of the entire thickness of the aluminum because the anodic layer is gone in the area we were examining. But what you see, and that red arrow is pointing to, is this giant pit where about 2/3 of the thickness of the aluminum has been eaten away by chemical exposure in this area. And it's pretty localized, right? It's not a huge area, but you've got these pits in this aluminum where your aluminum is locally almost eaten away. And that is going to severely affect the performance of these aluminum windows as they're more likely to degrade once the degradation has happened. So the client had also asked us about the deposits on the thin brick. So we got some samples and we see an area where we got some of the white deposit the client was concerned about. We looked at it using X-ray diffraction because that's one of the best ways to look at these types of deposits because they tend to be very crystalline and we can get a lot of information from X-ray diffraction. And we see some calcium hydroxide, which is not surprising, right? Because that mortar was freshly applied and we know that a Portland cement mortar, like concrete, is going to have calcium hydroxide, which can be leached from the water. We see some calcium carbonate as that calcium hydroxide reacts with carbon dioxide in the air and forms calcium carbonate on the surface. So what we see is really not unexpected. It happens frequently with new Portland cement-based material. It's often called new building bloom. But we also wanted to look at a different area of the mortar and understand about how much degradation it might be from the hydrochloric acid, and whether there's still chloride in there that could lead to additional corrosion of the aluminum. So in this case, we took a sample of the mortar, we ground it up, and then we did what's called a water extraction. So we mixed it up with water, stirred it up good, and then let stuff dissolve in the water, and then filtered out, so separated the liquid from the solid. And so the chemist who is doing this has been doing this for quite a number of years. And when she saw this, she snapped a picture and said, "This is not normal." So what we have here is we have this flask contains the water from that water extraction where it's been filtered down through a filter that you can't see in the photo. But she said, this is foamy. This is not normal. This is not what's expected. And that foaminess is an indication that there's still residual detergent from the cleaner in that mortar. So all of the cleaner residue has not been rinsed from the building. It is still there and can still interact with surrounding materials in the event of rain. And we did what's called a water-soluble chloride test on there and did find a little bit of chloride in the mortar, which can lead to accelerated corrosion of aluminum, but it wasn't a huge amount. So, from all these studies, what do we know happened? First of all, there was cementitious rundown on the aluminum that caused some corrosion. And the use of this acidic cleaner caused really severe damage to that anodized aluminum and ate away a good portion of thickness of the aluminum in areas. The efflorescence is typical new building bloom. You know, it can be a little hard to clean. An acidic cleaner will clean it right off, but we don't want to do that because this is going to damage your aluminum unless that aluminum is extremely well protected. But you can rinse it with water. It'll help a little bit, not a lot. You can brush it off, or you can just sort of understand that this is expected for this type of building. We also learned that cleaner residue remains in the mortar. So what did we tell our client? We said that masonry efflorescence will diminish with time, and it's cleanable, but it's also just sort of expected. They got to be very careful with acidic cleaners, which will remove the efflorescence, but if they're not thoroughly protecting susceptible materials, they're going to have the same problem. The aluminum cannot function as intended, and it's still a brand new building under construction. So it's not repairable. You can't put more aluminum onto your aluminum. You can't re-anodize in the field. You can paint it to make a uniform appearance, but you have pits and severely degraded aluminum itself that's, you know, going to be in various places and highly localized. So we recommended that they replace it all. And we gave them a procedure before they did that to rinse the remaining cleaner residue from the building in a procedure for looking at that rinse aid. And they did come to a confidential financial arrangement of who was going to pay for what. So I understand that these recommendations did help them come to an agreement. And with this, I'm going to turn it over to George to talk about some stone discoloration issues.
Thanks, Kim. I'm going to begin by discussing a project where we received discolored samples of travertine in the lab. These samples were removed from the exterior cladding of a coastal residential property, which began exhibiting localized yellowish to brown discoloration shortly after installation. Discoloration recurred after cleaning attempts, and our client was interested in A, determining the cause of discoloration, and B, to help aid in potential cleaning options. Potential sources of discoloration included external sources such as organics from material in contact with the stone or sources inherent to the stone. In this case, we were able to quickly determine that the cause of discoloration was related to the presence of known stain-causing minerals inherent to the stone using standard petrographic and chemical analysis procedures. So after conducting an initial cursory evaluation of the sample sent to us, we recommended conducting petrographic studies on a sample that encompassed the transition between the yellow to brown discolored and gray non-discolored surfaces like the sample in the picture to the right. Petrographic studies allow us to qualitatively characterize the stone-forming constituents in progressively finer detail to help aid in understanding the potential source of discoloration. Results of the petrographic studies showed that discoloration was superficial and not present at greater depths than 0.1 millimeter from the exposed surfaces of the stone when analyzing laboratory-prepared cross-sectional surfaces. The photo to the left is a thin section image showing the cross-section of a travertine sample in a region of discoloration with the outside surface facing upward. The yellow arrows point to discoloration observed along the exposed surface at depth in the sample, which was only superficial. The stone was identified to be travertine, and a characteristic feature of many travertine formations are the presence of large pores or cavities, which geologists call vugs, V-U-G-S, as shown with white arrows in the bottom right image. Vugs are generally accepted to form from the buildup of gases produced through the waste of microorganisms like bacteria or through the organic decay of plants or fungal matter. As a result, the remains of microorganisms often get trapped and fossilized in the pore space. The thin section image to the left shows brown-colored remains of fossilized microbial colonies lining a vug pointed to with red arrows. After observing that there was the widespread presence of fossilized microbial colonies lining bugs in the samples, it made sense to analyze bugs using SEM-EDS to determine their elemental composition. All the photos in this slide are examples of laboratory-prepared surfaces of the travertine sample taken using an SEM, or scanning electron microscope. The black spots in the top left SEM image represent pore space where higher volumes of microbial remains are present in the travertine sample. The corresponding top right elemental map shows that microbial remains are rich in manganese, which is a known stain-causing element. The bottom right SEM image shows an example of the morphology of the remains of fossilized microbial colonies encased by a bug. And the corresponding EDS spectrum to the bottom left shows that these remains are rich in the element manganese, abbreviated Mn. Other methods of evaluation that were not used in this case study, but may be helpful in stone discoloration analysis include X-ray fluorescence, which allows for more quantitative concentration measurements of the elements on the surface being analyzed. X-ray diffraction, like brought up previously, which identifies the crystalline components in the sample, or methods used to detect organic materials, such as GCMS and FTIR. In addition, we also performed comparative analysis at and away from discoloration using SEM-EDS to determine if there were higher concentrations of known stain-causing elements in discolored surface regions. Detectable concentrations of manganese were present on all surfaces, but discolored surfaces contained the highest concentration of manganese, and in some cases contained higher concentrations of the elements sulfur, sodium, and chlorine, which are commonly found in saltwater ocean spray as ions. Ions dissolved in ocean spray may increase the leaching potential and transport of soluble forms of manganese to the exposed surfaces of the travertine panels. So through our laboratory analysis, we found that the travertine samples contain bugs that are often interconnected and act as conduits for moisture migrations through the travertine panel system. Moisture access to soluble manganese within the fossilized microbial remains resulted in leaching of water-soluble manganese and deposition onto the surface. Near-surface manganese oxidizes to form non-soluble species of manganese that exhibit a yellow to brown color and deposit on the surface of the stone. The coastal environment exacerbates this problem as water with dissolved ions from soluble salts increased the ability of water to leach and oxidize manganese. However, it's likely that staining would have also occurred if the stone were exposed to non-salt water moisture just at a reduced rate. Because the manganese mineralization is inherent to the stone, the recurrence of discoloration is likely to occur following cleaning efforts. This type of discoloration is generally not observed in well-performing travertine sources commonly used in dimension stone applications. So the options that the owner had in this case study were either accept the removal of discoloration as a regular maintenance item, since cleaning is not able to address the source of discoloration at depth within the stone, or replace the stone panels with another stone or other material. So for our next stone-focused case study, we will be discussing another discoloration problem that occurred on a marble sculpture in a museum as a result of an adverse interaction with the cladding system components. Discoloration was reportedly first observed along the horizontal joint location separating marble stone units. Reportedly, discoloration started out faint and grew and became more intense in color as time progressed. The marble units were reportedly exposed to significant amounts of moisture during the fabrication process and were shipped on a boat from the stone fabricator in Europe to the United States in shipping containers that were not environmentally controlled. This is an example of discoloration occurring as a result of an adverse interaction with the built environment. Like our last case study, our client was interested in determining the cause of discoloration to help aid in potential cleaning options. Stone anchoring details indicated various anchorage types and dimensions for lateral attachment of the marble units, typically including discs, dowels, and bent plates that engaged curve slots cut into the stone. The elements in direct contact with the stone were type 304 stainless steel. The drawings show the curves and holes at stone attachment locations to be filled with sealant. Now, walls were reviewed using a field microscope at 11.5x magnification at both discolored and non-discolored surfaces of the marble units. Surfaces were also analyzed using a handheld XRF instrument, which allows for non-destructive elemental analysis of materials to provide identification and relative concentration measurements of the elements at and away from discoloration. Trace concentrations of iron were detected on both discolored and non-discolored surfaces of the marble units. Soluble forms of iron inherent to the stone have the potential to be leached by moisture and oxidized to form rust-colored iron oxidation products. Only trace concentrations of iron are needed to discolor light-colored translucent stones like marble. Chlorine was consistently detected at and away from discoloration. Dissolved ions in water, such as chloride, increase the ability of moisture to leach soluble forms of iron inherent to the stone, and can promote localized corrosion on the surfaces of metal elements in contact with stone units, such as stainless steel disc anchors or lead shims. The 300 series stainless steel, which was specified for elements in contact with the stone, is generally less susceptible to corrosion, but they are susceptible to crevice corrosion in the presence of chloride-bearing moisture in confined spaces. Now, the marble units were reportedly subjected to significant moisture exposure prior to installation in their current temperature and humidity-controlled environment. Migration of this moisture through the stone had subsequently occurred, as indicated by the bleeding of existing marker and pencil markings into the stone. Considering this moisture migration, holes and slots cut along horizontal joints in the stone at attachment locations allows for likely greater moisture accumulation and transport of either corrosion at embedments or inherent minerals, resulting in localized discoloration. The translucent nature of calcite marble makes it particularly vulnerable to pronounced discoloration. So through our field investigation, we found that the source of discoloration was iron. Iron was likely sourced from chloride-rich moisture interacting with stainless steel elements to form oxidized iron-rich corrosion products that were mobilized and transported to the surfaces of the marble units due to the saturated stone condition. Potential sources of chloride on the surfaces of the stone units include chloride from ocean spray during shipment, or potentially chloride that was introduced during fabrication process. Our recommendations for our client in this case study were to promote the drying of the stone units by setting the relative humidity of the room to a level between 55 to 60%, so that the units could completely dry before cleaning efforts. We also recommended that they conduct cleaning trials using the least aggressive methods to avoid causing damage to the marble unit surfaces. I will now pass it back to Kim one last time so she can summarize what we discussed today.
Thank you, George. So this overall summary of what we talked about some different mechanisms of degradation of materials, being adverse interaction with the building environment, which could be exposure to temperature or moisture conditions, incompatibilities with the surrounding material, and also just the construction and maintenance process. We've talked about adverse interactions with chemicals used intermittently, which may or may not be thought about when somebody is designing or specifying for a building. And problems that are inherent to the material itself, where the material just alters with time. Now, you've heard about some forms of this degradation can take months to years. It can have multiple steps involved. But some form of degradation can be immediate. You know, when the high pH or the acidic cleaner contacted the aluminum, that damage and degradation started immediately. But now that the damage has happened, it can be, again, more progressive because your material has been altered. A lot of these issues are aesthetic, but some of them can be structural or really affect the function of your material, which may require a different sort of repair or remediation. So you may be asking yourself, after hearing all of these case studies, how do you reduce your risk? So post-construction, you have a problem. You have a building facade and it's not performing as intended. There's some sort of degradation to the facade. So first of all is to get a detailed history. And depending on your function, you may not have that information readily available. If you're an owner of a building that was built 100 years ago, you're not going to be able to have project specifications. But talk to people, get some history about when the building was built, when materials were installed, and when the problem happened. And has it been gradual or has it happened all of a sudden? Maybe it's something somebody just looked up one day, you know, a tenant of the building and said, that doesn't look the way it used to. But get as much information as you can. And understand specifically what's different than expectations. Some materials do alter with time, and that's to be expected. Some metals, you know, copper, for example, it'll patina, and it's not intended, if left uncoated, to remain bright copper colored, you know, through its lifetime. But what's different than the expectations? And as you start this investigation, also think about what your goals are. Typically, they're what's going on, and more importantly, how do I fix it? How do I get my building facade back to the way I want it, back to its intended function and intended appearance? But as you can see, sometimes it's also a secondary or tertiary function to understand that any repair or maintenance is going to cost money, and whose responsibility is it to pay for that? And sometimes there's litigation involved. So it's important to understand what you're trying to do as you go about this process, because there's going to be some subtle differences between the processes. Involve the necessary parties, contractors, material suppliers, building owners, tenants. You know, figure out what they know and what they can do to help. Now, again, if you're looking to deal with financial issues and potential litigation, you may or may not want to involve them as soon as possible, depending on the strategy. And then sometimes it's helpful to have a specialist knowledge like a material science who may have a different or deeper understanding of the materials and their susceptibilities. And as you probably all well know, the best way to reduce your risk is to think about it before it happens. So in a pre-construction situation, you have many opportunities to reduce your risk. And first of all, you know, most of these issues have been just interactions with the built environment. So you need to understand your built environment and the various types of exposure you're going to have, whether they're constant or intermittent, seasonal, or you have construction in the building next door that's going to lead to greater exposure to abrasion, or your chemical factory has started and you have different chemical exposure. And also look at the other materials of construction and how they might interact with each other. And then you really need to understand your material performance. And if you're not a material scientist, how do you do that? One of the great resources is working with material suppliers and manufacturers. They probably know their material better than any, and have a lot of information about vulnerabilities and about where their materials perform well. Talk to your colleagues that you work with or through professional organizations and see what experiences they have. You may be able to find case histories. A lot of the case histories talk about problems because they're a little more interesting. But contractors and material suppliers will also have exemplar projects where they've had something that's worked well, and that can give you a lot of information. Again, sometimes having specialist knowledge or experience is really helpful. And if you're working with a newer material where you don't have case history or a new type of construction, you may want to consider doing some testing. And some of that may have already been done by the material supplier or the contractor, but figure out how something might interact with its environment and what information that can give you. And good planning can't prevent anything from happening, but it really can mitigate future problems. And we'd like to thank you very much for your attention.
Thank you, Kim, and thank you, George. We'll turn now to questions. And because we've run a little long with the presentation, we will extend the Q&A period past the hour by a couple minutes so that we can address more of your questions live on the line today. But if you need to drop off or if we're not able to get to your question, either Kim or George will follow up with you afterwards. So you can type your questions now in the Q&A box and hit submit, and we'll try to get through as many as we can. Okay, our first question. For an existing building project, I did moisture remediation, which involved a clear coat applied to rough face brick. Most of the building is okay, but I still have dark stains in a few spots. Any ideas on what is happening?
Well, that's a good question, and it's hard to say without actually seeing what's going on, but I can provide some speculation. First of all, when you apply a clear coat, it can alter the appearance of a material a little bit. It's sort of like when you get something wet. It has a different sheen, and sometimes inhomogeneities in a material can get highlighted by the use of a clear coat. Sometimes it can be differences in thickness of the coating layer have a little bit different visual appearance. Sometimes if you have localized debonding of a clear coat, even though the coating's still clear, it's going to look different if it doesn't stick to certain areas of your substrate. So off the top of my head, those are some 3 ideas, but obviously a little bit more detailed investigation would be required to really understand.
Okay, our next question. This is related to the acid-washed anodized case studies. So preliminary to your forensics, did you examine the original specifications and compare to product submittals? Were you able to determine if the product actually used complied with the specification?
Yes, so we were able to review some specifications and submittals, and there were nice specifications for the aluminum frames with a grade of anodic layer, and we were able to look at undistressed areas and confirm that the aluminum itself, the anodizing layer, did meet that specification. However, there wasn't a written specification for the cleaning procedure, so we were only able to get a history of what was done and what product was used. But we weren't able to comment on whether or not that met specifications because there wasn't a specification, which certainly would have been very helpful had somebody anticipated that this might occur.
All right, our next question. Does the petrography work also extend to stone type identification and possible quarry sources and locations?
Well, to the first part of that question, yes, we often conduct petrographic examination to identify the stone type of the sample that our client's interested in, but we also go an extra step and comment on any potential durability concerns associated with the sample, and we'll often be involved and conduct, very elaborate strength programs, stone testing programs to understand strength in service in our laboratories here on many high-profile projects that come across the lab. So as it relates to quarry sources and locations, a lot of stones look the same, so it can be more difficult if we don't have documentation of where the stones were purchased, or we're lacking information on that end. But we definitely can look at a stone type and see if it's consistent with a certain quarry source. So run a comparative examination.
Okay, our next question. Have you ever been asked to personally testify in court to report your findings during litigation?
Well, I can answer that question. So as part of our work, we do sometimes get involved in litigation procedures. I've been asked to testify in deposition many times. Every case that I have been involved in has settled prior to trial. The most recent case settled after trial began and before I took the stand. So I have not yet been required to testify in court, but it is part of the process when things do get contentious.
Okay, this next question is, does this weaken the glass? So related to the glass case study.
Okay, so I'm not sure if that question is related to the original deposition or the potential polishing. The original problem is very superficial, so it affects the ability of glass to serve its function because it's supposed to be transparent, and it's no longer transparent, but the deposition and even that alteration of the glass itself is only just at the very surface, so it doesn't weaken the glass. However, a polishing process done to clean and remediate the issue has to be done properly and with qualified contractors, because in that case, you could over polish the glass and cause some additional issues if it's not done properly.
Okay, our next question, and Kim and George, you'll have to remind us which case study this question is related to. The question is, to avoid the deposits in the first place, would more adequate drip edges have averted the problem?
Well, that is a good question, which case study that goes with. But when you have potential for water to interact with your materials of construction, having drip edges and really controlling that water flow, whether it comes to deposition on glass or some efflorescence issues, can be really helpful. It's a way of controlling your built environment. George, I don't know if that would be helpful when it dealt with the discoloration, for example, of the travertine.
Can you repeat that, Kim?
If you had drip edges to help control rainwater and liquid water on the surface in the construction, would that have helped or affected the discoloration of the travertine?
It likely it has the potential to decrease the rate of discoloration, but the fact that those travertine panels were installed next to a bayfront environment, the relative humidity and ocean spray alone will likely allow for moisture to drive through the stone and cause the staining and after cleaning recurrence of discoloration in service. So it likely wouldn't help in that scenario, no.
Okay, our next question. Would you get similar damage to a Kynar finished aluminum with acid cleaners?
Okay, so this person I think is talking about the damage to the anodized aluminum with the acid cleaners. So a lot of times aluminum is finished with a fluoropolymer type coating instead of the anodic layer. And the fluoropolymer coating itself should be pretty resistant to acid. That's one of the requirements of getting a particular, what used to be AMA certification or compliance with an AMA standard, which is no longer AMA. I think it has a different name now. But the coating can only protect the aluminum where it exists. So if there's defects in the coating, if the coating is scratched, if you have cut edges that are no longer protected, if you have holidays or pinholes in the coating, then that acid is basically in contact with the aluminum and you can have issues.
Okay, we've got time for one more question. How do you determine recommending cleaning procedures versus replacement?
Well, I would say that depends on both the degree of degradation and distress, as well as client, building owner, or tenant requirements. So if a material is degraded to the point where it's currently not serving or may not serve its intended function in a while, so if you're getting holes or pits in a material, it's not going to serve its function, and there you might want to consider replacement. If we think cleaning can get the material back to its original function, that's going to be much more cost effective. But you may have ongoing maintenance that the client may or may not want to take on and may choose to replace if that's a more financially sound investment for them.
All right, thank you, Kim, and thanks, George. That was a great presentation. We appreciate you all hanging on the line with us for a couple more minutes to get through some of these questions. We hope the whole webinar has been educational. Thanks so much for joining us. If you have any questions about the topics covered today, please don't hesitate to reach out to either Kim or George. They'd be happy to answer your questions. And if you have any questions or comments about the WJE webinar, please don't hesitate to reach out to me, Liz Pimper, at lpimper@wje.com. So again, thank you so much for your time today, and we hope you have a great rest of the day.